Using Python for some data analysis. This is basically going through parts of the notebook that is provided to you for graphing and finding a good fit function. For starters, you need to have a file that has the data in it. Here I'm going to assume something similar to a free fall experiment, so I have time, and then commas, and then position, and then commas, and then the uncertainty of position. So I have 3 columns. What you have will depend on the experiment that you're doing. And you need to know where to find this on your computer. So this is comma separated values, or CSV. Okay. Your instructor will have given you access to the notebook, and you'll need to download it onto your computer and upload it into Collaboratory. The purpose of this is not for you to just make changes and then turn it in, but to copy the code that you need. All of the text that is here is to explain the usage of the code, and it is not really appropriate for this text to be in the file that you turn in. So we won't be using all of this. So we are going to use the part where we import files and plot things. So this first code cell is appropriate. I will copy it. And I will make myself a new notebook. And paste that block of code there. Give it a name. And save early and often. Probably what you'll want to do at some point is to download the IPYNB. That will download the entire notebook to your computer. For now, I'm just going to save it in the cloud. The nice thing about Collaboratory is you can run each of these code cells separately. Now I'm just going to be adding code cells. You will need to add text cells to intersperse to do whatever level of explanation your instructor wants. But what I want to do next, I am going to use the Google Collaboratory, upload the files onto the cloud, and then read it and analyze it from there. So I need this cell that will upload the file from my computer. Copy it, paste it. When you run it, you will need to click on Choose Files. And I happen to be in the right place. Click on it to select it, open it, and it has uploaded it. To check that it's there, if I go on the left and click on the folder here, it is showing up. Okay, so I'll set up another code cell. Now I need to actually define the file name. So I'll first copy this and paste it into a new code cell. You have to actually tell the computer the exact name of the file, which is up here after the previous code cell. So it has said saving test data for analysis.txt2, and it's the stuff after the 2 that I want to copy. And I want to paste that inside of the quotation marks. The quotation marks need to be there. So now it knows file name, and later in the program I can just type file name instead of having to type test data for analysis.txt all the time. So run it. So far so good. Now we have to actually read the file in a way that the later code can understand. So I'm going to copy this next block and make a new code cell, paste it in. There's a couple things we have to check on. First, to the left of the equals are, in this case, 3 variable names. And that's appropriate because I created a file that had 3 things: the time, the position, and the uncertainty. So we're okay on the left. On the right, the main thing you have to look at is the delimiter. If you created a CSV file, as suggested, then that delimiter between the quotation marks needs to be a comma. Then I have it print each of these 3 arrays. These are going to be NumPy arrays, just to make sure everything's working okay. And there's one weird thing that might happen. So we run it, and everything's good. I have a small file, all the arrays are okay. Sometimes one thing that can happen is the very first element of the very first array could say NaN. I don't think it's going to let me type it in. Oh well. If it says NaN, that means not a number, and then you will have to replace that with the actual number. If you do have to do that, that would look something like this. It's the time array that's first. The first element is 0 because Python starts counting at 0. And if it were not showing up properly, I would say that that equals 0. I will not run that cell because I don't need to. Okay. So the first thing you should do is plot the data. Before you go to analysis, you need to know what you're analyzing. So this next code cell contains a bunch of commands to plot the data. I will copy it over and then see if I need to make some changes. So it's going to plot time, position, and the error bar. And for the error bar, it's going to use the uncertainty of the position. That's good. Format BX, you can play with that. Title is falling object, so that's a useful thing. Y label, position, X label is time. If you're doing a different experiment, such as one involving voltage and currents, you will need to change all of these. Also, if you have uncertainty data, that means you should also change these array names up here so that they match the experiment you're doing and you keep track of things. If you have uncertainty of other variables, you should put that in here too. Okay, so this should be good. And there it is. The error bars are relatively small. And I look at that and I say, that looks like some kind of curve. I would not want to fit this to a line. But let's guess, I don't know, a parabola. So you need to actually define the function that you think mathematically fits the data. In the notebook I gave you, there are 2 sample functions. Linear func is a straight line. It has slope p1 and intercept p2, not appropriate. Skew func stands for square root. It uses the NumPy square root function. You want to use the NumPy for all math functions for things to work properly. And again, that is not appropriate. The square root kind of turns over, and this looks like it keeps going up and is getting steeper. So I need something different. But I can still use this template. So I'm going to copy this just as a template, but I'm going to change everything in it. Okay, first of all, I don't want square root. Okay, skew func, I guess that could mean a square. So we're okay with that. Maybe I'll call it square. Okay, now in these functions, the first argument here is going to be the array of your dependent variables. So in this case, it's going to be time, but it doesn't really matter what you call it here, because within the function, everything just stays within the function. In this case, the next 2 things in the square root function represented two parameters, one that multiplied the square root and one that was added to everything at the end. And the straight line would also have two things here, a slope and an intercept. For a parabola, though, you need three things. A, B, and C are the traditional names. So I have to completely redo this next line, which is actually going to calculate the function. Looks like I lost a B up here. So traditionally, A multiplies the x squared. And to do a square, you need two asterisks and a 2 to do a power. Plus B times x. And again, x here is just a name that only exists within the function. It's going to be your independent variable. Plus C. Then this final line, return y, is what later will send the calculated values to the rest of the code. Okay. Now, in addition, I'm going to do something that was done in the notebook, and that is just test the function. To test the function, you can say print, and inside parentheses, you tell it what you want to print. What I want it to print is the value of the function square, func. I have to give the whole name, and then I have to send it these four parameters. So let's say x equals 1, a equals 2, b equals 3, c equals 4. Let's see here. So 1 squared is 1. So 2 times that is 2. Plus 3 times 1 makes 5. Plus 4 makes 9. So if everything's working, this should print 9. Yay. Okay, so again, this was the function that the later code is going to try to fit to the data. Is this function a good mathematical description of this data? And it will perform the fit, and it will find these parameters A, B, and C that best match the data. Okay, so I'll go back to the reference notebook, and this next block does that work, and I'm just going to copy it and then make changes when I get it into this particular notebook. So the function we defined had the argument x, which is the independent variable, and then the parameters a, b, and c that multiply x squared, x, and c. So the first line here, param, needs to have three numbers. One for a, one for b, one for c. And these are just your initial estimates. You say, looking at the graph, what's a good, reasonable guess as to what a, b, and c are? And then the later code will calculate what they actually are to best match the data. So I look at this, and it looks like c is pretty small. I'll call that 0, so I'm going to put a 0 at the end here. B is kind of related to how the function is tilted at the beginning. That looks pretty small, so I'm going to call that 0. And A, okay, well, when I go from 0 to 3, 3 cubed is 9, and it looks like it's about 9. So I'm thinking A is probably close to 1. So again, these are initial ideas of what's going to happen. This next line is going to do the work of finding the A, B, and C that best fit, and also the uncertainty of A, B, and C. So here we go. And it runs, and it runs, and it runs, and it says linear func is not defined. Well, that's because the function, one of the things that you feed into the fit function, so optimize.curveFit is the function that does the fit. You have to feed it the name of the function you want to fit, and I did not define linear func. I defined square underscore func. Well, we're here. Let's check these other things. Time, that's going to be the independent variable that gets fed to the function. It will take the place of x up here. And then it needs the data, the time data. Well, the data, yep, that's an independent variable. It needs the dependent variable data, x pos, the position. It needs a list of initial parameters. And it also needs to know your uncertainties because that's part of the fit. Okay, so let's run this again. Roughly speaking, these first three numbers are the best fits for A, B, and C. And the diagonals of this matrix down here are related to the uncertainties. But to make it easier to understand what all of that means, the template notebook has some code. I will copy it over and then make the changes that are needed. Okay, so we're not doing slope and intercept. That's the first thing that needs to change. So the first parameter was A. The second parameter was B. The 0, 0 here, 0 refers to the first parameter. Python starts counting at 0. The 1, 1 refers to the second parameter. The square root is how the uncertainty is calculated as the uncertainty of the diagonals. The units we should think about. In this case, if you think of the acceleration equations, this is meters per second squared. And B is meters per second. And I need one more line for C, so I'm just going to copy this one. Go to the end, hit enter, and paste it. So now this is going to print C. I need to change the 1 to a 2. This will do the third parameter, and I need to change these two ones also to 2. So now it's doing the third parameter, and the units of C are just meters. And there they are. It's telling me that this is probably a pretty good fit. If I compare the uncertainties with the values, the uncertainties are less than 10% at worst, a little under 10% at best, maybe 2%. And that's one sign of a good fit, is the uncertainty of the parameters is pretty small. There's way too many digits here. You would round it if you actually wrote this down and reported it. So, the computer says that's a fit. Never trust the computer. Again, I will copy this line. I'm not going to copy the print line. I don't think I need it. And I will change it appropriately. This time I'm going to remember to change it to the square function. Square func. So what this is going to do is it's going to take that square func, feed it time as the independent variable. Then it will feed it the three best parameters. I have best param 0, best param 1, so I have to add best param 2. So it's going to feed square func, the independent variable, the time array, and then these three parameters, and it will do the calculation of what it thinks the fit is, what it looks like, and it will call it xfit. And no error messages, so far so good. The purpose of that is to let you come down here and redo the plot, but also include the fit. So I will copy that. I will paste it here. I'm going to change the title. This was not a moving cart. This was a falling object. And it's going to plot two things. It's going to plot the data again. This is the line we had before. It's going to label it data. And then this next line will plot the fit. And the stuff in the quotation marks here means it will do it as a red line. And then we have various labels. It will print a legend and so forth. And it draws the line point to point because that's how it does it. It is basically calculating the best fit at each data point and then drawing a red line between them to kind of guide the eye. And that matches what I would call the eyeball fit. That is a good fit. But there's something you can do to make that quantitative. Under comparing fit functions, there is some code here which will print something called chi-squared, and I will modify it to print chi-squared and reduce chi-squared. So paste it in here. Degrees of freedom, that is the number of data points minus the number of parameters. Chi-squared is what is minimized to do the fit. It's basically the difference between the data points and the fit points within the range of uncertainty. So chi-squared should be roughly equal to the number of data points. Reduced chi-squared is another number that's useful. It's mainly useful if you're comparing two different functions. In both cases, you want chi-squared and reduced chi-squared to be as small as possible. So I'm going to print both chi-squared and the reduced chi-squared. So the chi-squared was around 20. 5 would be better. The reduced chi-squared is around 10. These numbers are fairly large because in my original data file, when I set the uncertainties, I wasn't really careful. The uncertainties are probably a bit small, either that or I didn't quote enough digits and measure the numbers as accurately as I could have. This is basically saying that the uncertainty in the numbers for the actual data is bigger than the measurement uncertainty. So that's why the chi-squared and reduced chi-squared are so far off. This will be an indication you could maybe improve things by taking the data with more precision. And the rest of this is not really needed for now. So, of course, you save this early and often, and at some point when you're done, you should probably download the whole notebook to your computer. If you save it as IPYNB, then it saves the entire notebook, including any text cells you have. When you want to send it to an instructor, you can click on Share over here. And basically, you need to make sure, if you want your instructor to see it, say anyone with the link, and then you can copy the link and send it to your instructor through whatever means, and it will send your instructor this entire thing. You can set it up so your instructor can either view it or so that your instructor can make comments, or so that your instructor can actually be an editor. That will be up to your instructor. And there you go.